class, let's talk about induction. Many of you have used induction before, but let's start from the basics so that we can talk about weak versus strong induction. So say A is a set, and we want to show that J is in A for all J between 10 and 1. We want to show that the elements 1, 2, 3, etc. up to 10 are in our set J. You could show that J is in A for each individual J. That is, you're going to show that 1 is in A, 2 is in A, all the way down to 10 being in A. Or you could use a principle of induction. That means establishing two things. That 1 is in A, and that for every J in A, J plus 1 is in A. This first part is called the base case, and this second part we call the inductive step. Now, why does this work? Well, first, we independently establish the base case, and that, of course, gives us that the set A, at the very least, contains 1. And then we apply the inductive step. And that gives us that the fact that 1 is in A implies that 2, which is 1 plus 1, is in A. And thus we get A contains the set 1, 2. You apply the inductive step again. 2 being in A will give us that 3, which is 2 plus 1, is in A. And that tells us that A contains 1, 2, and 3. And you continue along the way to the final inductive step, where 9 being in A will imply that 10 is equal to 9 plus 1 is in A. And thus we get that A contains 1 through 10. Shown a little bit differently, the base case gives us that 1 is in A, and then the inductive step gives us that 2 is in A, then 3 is in A, etc., until all of them are in A. Let's do an example. An inductive argument. So we're going to show that 0 plus 1 plus 2 plus all the way up to n is equal to n plus 1 over 2 for all natural numbers n. The base case is that n is equal to 0. And here we can just note that 0 is equal to 0 times 0 plus 1 over 2. Next, we're going to assume the inductive hypothesis. That is, we assume that the statement that we want holds for some k in the natural numbers. So we're going to assume that 0 plus 1 plus ... up to k is equal to k times k plus 1 over 2. And then the last part of our inductive argument is that we have to do the inductive step. So assuming the inductive hypothesis for n is equal to k, show it holds for k plus 1. Here, we're going to add all the integers from 0 up to k plus 1, and we're going to notice that from the inductive hypothesis, the first k plus 1 terms from 0 to k is equal to k times k plus 1 over 2, and then don't forget to add the k plus 1. From here, it's just algebraic manipulation. This is going to be k squared plus k plus 2k plus 2 over 2, which turns out to be k plus 1, k plus 2 over 2. And with these three parts of our inductive argument, we have proved the statement for all n. This is the induction that you're probably used to. This is weak induction. Let's talk about the principle of strong induction. Here it is. Let A be a set of natural numbers. If 0 is in A, and for all k in n, if 0 up to k is in A, then k plus 1 is in A. If this is true, then A is equal to the natural numbers. You're trying to prove something holds for all natural numbers. You take your base case, which is 0 is in A. Instead of assuming that it just works for k and using that to prove that it works for k plus 1, we actually assume that it works from 0 all and for every number up to k. And then it implies that it holds for k plus 1. The difference between strong and weak induction, in essence, is the difference between what you're assuming in your inductive hypothesis. Are we assuming that the statement holds for k and then using that to prove that the statement holds for k plus 1? Then you're doing weak induction. If you're assuming that the statement holds for 0 all the way up to k, and then you're proving that the statement holds for k plus 1, then you're doing strong induction. Let's do a fun visual example of this. Example. Show that for n greater than or equal to 6, a square can be dissected into n smaller squares. So let's play around a little bit before we get down to business. How do you break up a square into smaller squares? Well, there are some standard ways of doing it. So, it's not too hard to get 4 by bisecting each side. And then, so you can imagine getting all square numbers pretty easily. So let's cut our sides into 3. This is how we get 9. We can cut our sides into 4s. That's how we get 16. Pretend that these are squares, etc. So how do we get 6? Let's do our base case. N is equal to 6. Well, I'll do this by demonstration. I'll prove it directly. So here is our square. All we have to remember is that we don't actually have to have all squares being the same size. All right, then we're going to assume our inductive hypothesis. Assume that a square can be dissected into n squares for all n between 6 and k. Then we have to show that it works for k plus 1. All right, if k plus 1 is 7, then we can do it like so. We can split our square into 4 and then split one of those squares into 4 in the way that we illustrated before. Otherwise, note that by the inductive hypothesis, the square can be dissected into k minus 2 smaller squares. Take one of those smaller squares and dissect it into 4 in the standard way. We get, well, we started with k minus 2 squares, and then we added 3 by dissecting one of the squares into 4, and that is k plus 1 squares. All right, and that proves it. This is an example of strong induction because it didn't just rely on the case step, it also relied on other steps being true before. Next class, we're going to talk about the principle of inclusion-exclusion.